Hello, in this video I will provide a brief introduction to quantum mechanics. One of the earliest quantum mechanical experiments was performed during Young's double-slit experiment, and this was to determine the diffraction pattern of waves. The idea of this experiment is that sending light through two slits creates two sources of spherical wavelets. And this forms an interference pattern on the screen, as waves from the two different slits have to travel different distances to get to the same point on the screen, meaning that they're on different points along the wave. So at some points they may interfere constructively and at other points destructively. However, if the intensity of light is lowered, we see at some point the interference pattern does not emerge immediately. Instead, there are distinct points on the screen that register hits, carrying distinct values of momentum. Over time, the hits register into the interference pattern that we know, but this is not obvious immediately if the intensity of light is lowered. This also translates to electrons. Electrons are sent through the double slit with a very low intensity, let's say once a year, 1 electron per year. So this eliminates any interaction between any electrons. Electrons will register distinct hits on the screen since they are particles, but over time we see that an interference pattern arises. This is completely unexpected for electrons, which we believe are particles. We expect to see two distinct collections of electron, one that went through slit 1 and one for slit 2. In conclusion, light was a wave that does particle-like things in that it registers hits with discrete values of momentum when sent through low enough intensities, and electrons are particles, but they do wave-like things in that they create an interference pattern over time when going through a double slit. So to solve this problem, de Broglie proposed the wave-particle duality in 1924. This idea says that all matter can exhibit wave-like properties as well as particle-like properties. For example, the electron exhibits an interference pattern, which is characteristic of waves, but also hits the screen in localized values of energy and momentum, which is a characteristic of particles. The wavelength is Planck's constant over the momentum. This reveals why the wavelength of macroscopic objects are not seen. For example, a baseball with a momentum of 1 kilogram meters per second would have a wavelength on the order of 10 to the negative 34 meters. This is way too small to measure. Even an electron traveling near the speed of light only has a wavelength on the order of 1 picometer, or 10 to the negative 12, compared to on the order of 100 nanometers, or 10 to the negative 7 meters, per visible light. Therefore, to even see the interference pattern of electrons, one must use specialized equipment such as a crystallized grating with much smaller slits. In classical momentum, a state of a system can be completely defined by identifying its position and momentum. This describes a system with all the details that are needed to know right now. Dynamics, which includes Newton's laws, can describe how the system changes with respect to time. With wave-particle duality, each particle can be assigned a wave function that gives all of the quantum mechanical information needed to define a state. But this poses a new question. Wave function for light is the electric field, but what does it represent for other particles? Max Born's principle says that the square of the wave function describes the probability of finding an object at a location. In quantum mechanics, wave function can be real or complex valued. Only their squares, or the complex conjugate times the wave function, needs to be real. The square of the wave function times the volume element gives the probability of finding the particle in that volume. Usually, quantum mechanical differential equations are linear, meaning multiplying a solution by any constant is also a solution. But the probabilistic interpretation solves this by placing restrictions on allowed wave functions. Namely, if a particle exists, integrating the probabilities over all space should confirm the particle exists somewhere, so this means a probability of 1. This process is known as normalization, where you set the integral equal to 1, and then this way you could solve for the constant in front of the wave function. Since wave functions represent probability, we have two different types of unique states. Number one is the state of definite position. The wave function looks at a spike at this position, and this means that multiplying the wave function by all positions gives back the original position of the particle, since that's pretty much the only place where the wave function isn't zero when multiplying things. A state of definite momentum is a complex valued oscillatory function, but its square is actually a constant value, meaning the probability of finding the particle does not depend at all on position. Multiplying the wave function by negative IH bar times the derivative of the wave function with respect to x should give the momentum in this case. States of definite position and momentum are contrived, and in reality, most wave functions are usually mixtures of the two states. While historically, quantum mechanics was not first well received by leading scientists such as Einstein, its predictions agree with experiments. In addition, quantum mechanical theory has led to many successful applications, including nuclear fission and fusion, configurations of electrons in the elements, lasers, semiconductors, and computing. Thanks for watching.